All of you are familiar with glucose, right? What do you know about this molecule? Well, glucose is a small, simple sugar that serves as the primary biological fuel for energy production in the body. It is essential to perform the metabolic functions that sustain life. Besides, it serves as a building block for larger structural molecules of the body. Do you know how glucose accommodates these diverse properties to carry out manifold functions? The properties and reactivity of a molecule are largely influenced by its structure. In this video, you will learn about the structure of glucose. Let us start our discussion with the preparation of glucose. Glucose can be obtained by two methods. The first method is the acidic hydrolysis of glucose in an alcoholic solution. This method gives an equal amount of fructose along with glucose. The second method gives glucose exclusively. This involves acidic hydrolysis of starch at 393 Kelvin under 2 to 3 atmospheric pressure. Next, let us learn the structure of glucose. Various chemical analyses were done and the molecular formula of glucose was found to be C6H12O6. Once the molecular formula is known, the structural formula of glucose can be obtained on the basis of reactions given by glucose. Now, let us elucidate the structure of glucose based on the experimental observations. When glucose was heated with hydrogen iodide, the product obtained was N-hexane. Hexane is a straight chain compound. Hence, the formation of N-hexane suggests that all the 6 carbon atoms in glucose are linked in a straight chain. Next, let us identify the functional groups present in glucose. When glucose was treated with hydroxylamine, it gave oxime as the product. Moreover, glucose upon reaction with hydrogen cyanide gave cyanohydrin. Oximes or cyanohydrins are formed only if the carbonyl group is present. Thus, these reactions confirm the presence of the C double bond O group in glucose. Our next question is whether carbonyl carbon is aldehydic or ketonic. To identify this, let us find out how glucose reacts with bromine water. Glucose in the presence of bromine water is oxidized to gluconic acid. Bromine water is a mild oxidizing agent, and if it could oxidize glucose, then it indicates the presence of an aldehydic group rather than a ketonic group. Now, as we have confirmed the presence of the aldehydic group, let us find out if any other functional group is present in glucose. See the reaction of glucose with acetic anhydride. The formation of pentaacetate confirms the presence of 5 OH groups in glucose. The stability of the compound is a clear indication that 5 hydroxyl groups are attached to different carbon atoms. The next question is, are these alcoholic groups primary, secondary or tertiary? To identify the type of alcoholic group, consider the oxidation of glucose and gluconic acid. Interestingly, both give saccharic acid as a product. The formation of this dicarboxylic acid clearly indicates the presence of a primary alcoholic group in glucose. Thus, based on these observations and many more experiments, the exact spatial arrangement of glucose was given by Fischer. Moreover, the dextrorotatory nature of the molecule has been represented with a plus sign. Besides, the letter D represents the relative configuration of glucose based on the configuration of glyceraldehyde. However, this structure had some limitations. If the glucose had an open structure as mentioned here, then it has to give reactions of aldehydes. But glucose neither gave Schiff's test nor an addition product with hydrogen sulfide. Also, pentaacetate of glucose does not react with hydroxylamine. This indicates the absence of any free CHO group in glucose. Further, glucose exists in two different crystalline forms, alpha and beta. The alpha form of glucose was obtained by the crystallization from a concentrated solution of glucose at 303 Kelvin, while the beta form was obtained by crystallization from a hot and saturated aqueous solution at 371 Kelvin. In order to explain the above mentioned experimental observations, a modified structure was proposed for glucose. Now, Let us have a closer look into the cyclic structure of glucose. Here, glucose forms a 6-membered ring in which OH at the C5 is involved in the ring formation, as you can see here. This OH group adds to the CHO group. This gives a cyclic hemiacetal structure. This clearly explains that CHO group is absent. Thus, glucose exists in two forms. In analogy with pyran, the cyclic structure of glucose is called pyranose. See, here these two cyclic forms differ only in the configuration of the hydroxyl group at C1, as you can see here. Such carbon atoms are called anomeric carbon, and these isomers are anomers. These cyclic forms of glucose exist in equilibrium with the open chain structure of glucose, as you can see here. As we have completed the discussion on glucose, next I would like to introduce yet another important monosaccharide, that is fructose. We will learn the structure of fructose and many more carbohydrates in our next video. With this, we will summarize the video.
Manorama Horizon. Learning made simple.